Okay, so last time you guys learned about basic right triangle trigonometry, and you learned about how it's really based on similar triangles, right? So, for example, here you have two similar triangles, and you can see how they're the exact same shape, right? You see they have the exact same angles, the exact way that the lines meet each other, the exact same shape, but they're different in terms of size because you learned about how they're angle measures are always the same, but their side lengths might be doubled, tripled, or multiplied by some other ratio. So indeed, you can see here that A and D are the same ratio as B to E, right? And you'll see that maybe if D was 2 times A, then side length E would also be 2 times side length B. So why is this relevant to trigonometry? Well, because since similar triangles always have the same angles, but also the same side ratios, that means we can set up a series of functions such that their input is an arbitrary angle between 0 and 90 degrees. So in particular, you know that if you have a right triangle and an acute angle that is somewhere in this right triangle, you can define sine of x to be the opposite length over the hypotenuse, the cosine of x to be adjacent over hypotenuse, and tangent of x to be opposite over adjacent. So in this case, x would be over here. And once again, the function you have here will be a unique value because, for example, let's say that you make another right triangle here. You see like this pink triangle I have here. So obviously you can see that it also has an angle of x, right? But then the thing is, sine of x will be the same for this pink triangle x as it would be for the bigger gray triangle x. Why? Because when you take sine of x in the gray triangle, you have this length over this length. But since this gray triangle is similar to the pink triangle, that means their side ratios. In other words, the ratio of this length to this length to this length to this length will be equal. In other words, sine of x will be a consistent value no matter which triangle it is that you take the x. Does that make sense? Jasper, does that make sense why we can define triangle relationships and have them be unique values? A little bit. Okay. All right. Well, let me know if there's anything you doesn't quite understand. But once again, the basic idea is that since when you have a similar triangle, here, let me give you another diagram. If you have two similar triangles, here, you have two similar triangles, and these two triangles both have a common angle x that is the same. So let's say these are my two triangles, and they both have an angle of x. Actually, in particular, let's call this one 30 degrees. So this right triangle has a 30-degree acute angle, and this right triangle also has a 30-degree acute angle. Then if I call this side length A, this side length C, this side length B, and this one E, F, and G, then by similar triangles, you know that A over B would be equal to E over F, right? But then if you look at this definition of tangent over here, you can see that A over B equal to E over F is actually equal to the tangent of 30 degrees, right? So you can see that no matter what kind of a triangle as I use, as long as it has an angle of 30 degrees, it will have a consistent value of tangent. So if I have a triangle like this big, but then the angle inside here is 30 degrees, then this side rate over this side length will be equal to a over b, and thus equal to the tangent of 30 degrees. Does this make sense? Yes. Okay. Joyce says yes. Okay. Well, let me know if you have any other further questions. But anyways, the bulk of today's class is actually more about the unit circle definition, because as you can see, if you use the right triangle definition, all of these functions, sine, cosine, and tangent, are really limited to acute angles, right? But then if you have the unit circle, you can actually extend the definition, because now instead of being only limited to acute angles, you can now go angles like this. Sorry, that's not a very good line. You can now go with angles like this. What? Sorry. You can now go with angles bigger than 90 degrees. For example, you can have an angle of maybe, what is this, like 120 degrees? And then you would simply go around the unit circle and end up at this terminal point here. And then you would define the cosine and sine of 120 degrees to be the coordinates of this point. So in other words, what we're doing here is that you rotate a point. In particular, you rotate the point 10 a certain number of degrees counterclockwise, right? So let's say you have an angle of 30 degrees. Say this is 30 degrees. Then what happens is that you take this point 10 and you rotate it 30 degrees counterclockwise along the unit circle, right? You rotate it and then you move it along the circle until this angle here is 30 degrees. And then you define cosine and sine to be the x and y coordinate of this resulting point. So for example, in this example diagram here, you can see that if you have an angle of theta and you rotate 10 theta degrees around the unit circle, you end up with this point, xy, and thus we define cosine to be the x coordinate and sine to be the y coordinate. And again, this way we can now calculate cosine, sine, and tangent for any arbitrary angle. We can even do negative angles, because if you have like an angle like this, then you what you simply do is that instead of rotating counterclockwise, you now rotate clockwise. So for example, this would be an angle of negative 30 degrees. And then cosine and sine of negative 30 degrees would simply be the x and y coordinates of this point. Does that make sense? Yes. Okay. So moreover, something interesting you would see is that, remember how tangent is opposite over hypotenuse, right? But then you'll see that in this case, opposite over hypotenuse is simply sine over cosine. And this actually really matches what we learned earlier, because last class you should have learned that tangent of an angle theta is actually equal to sine of that angle over cosine of that angle. Also, if you know a little bit about slopes, you would know that slope is rise over run, and thus tangent of an angle is actually just the slope of this line here that it corresponds to. So for example, here with this angle, the tangent of theta would be the slope of this, and thus the change in the y direction divided by the change in the x direction. So hopefully that makes sense. Let me know if you have any questions. Do you guys have any questions? Does this all make sense? Is anything not making sense? Anything that's confusing? If so, let me know. But if not, we're gonna now go over the roadmap or like what we're gonna do in this lesson, right? So basically today we're gonna talk about 2 ways to prove the Pythagorean identity, which happens to be one of the most important relationships that you would study in trigonometry. So now we'll go over the first proof, and in both of these, they require a little background knowledge and other stuff. So we'll cover that before we go on to the proof. So here's the first proof. We have to first know the Pythagorean theorem, which simply states that the sum of the square of the legs of a right triangle is equal to the square of the hypotenuse. In other words, a squared plus b squared equals c squared. Let me show you a brief example. Let's say I have a right triangle shaped like this. Let's say that this side length is 3, this side length is 4, and then this side length is 5. And moreover, we know that this triangle is a right triangle. So here it's a right angle. So then by the Pythagorean theorem, we should have that 3 squared plus 4 squared is equal to 5 squared, right? But then if you evaluate this, you'll see that 3 squared is equal to 9, and 4 squared is equal to 16, which adds to 25, which happens to be 5 squared. So you see that this is really the central idea of the Pythagorean theorem. It's simply a relationship between the side lengths of the legs of a right triangle and the hypotenuse. So again, it's simply the sum of the square of the legs of a right triangle is equal to the square of the hypotenuse. Does this make sense? Do you guys have any questions about this? Jasper, does the Pythagorean theorem make sense? Do you guys want another example? Joyce, do you have any questions about this? No questions? Okay, so why are we talking about this? Well, here's why. So as you saw previously, since the coordinates of the terminal point of an angle are cosine theta and sine theta, you see that cosine theta and sine theta will thus also correspond to the lengths of this right triangle, right? So this is cosine theta, and this is sine theta. But then since this is a right triangle, and we know that the hypotenuse is always 1 because we're talking about a unit circle, we know that this value squared plus this value squared is equal to this value squared, right? So in particular, you know that cosine squared plus sine squared is equal to 1. So this is known as the Pythagorean identity. And thus, given the cosine of any angle theta, you will be able to calculate sine theta by plugging in one of the values and solving for the other. Does this make sense? Jasper, Joyce, do you guys have any questions about this? Does this all make sense? Do you guys have any questions?
No.
No? Okay. All right. So then we're going to talk about a second proof that is slightly more complicated. So to begin understanding this proof, you have to first understand the distance formula, which is really just another way to look at the Pythagorean theorem, right? Because the purpose of the distance formula, like the goal here, is that if you're given 2 points x1, y1, and x2, y2. You want to know what the distance d between them is, right? You want to figure out what this distance is. But since you know the Pythagorean theorem, what you could do is you could construct a right triangle by dropping a perpendicular down to here and extending a horizontal line over there. This will then give you a right triangle, so you can apply the Pythagorean theorem, right? Because if you have 2 points x1, y1, and x2, y2, and you want to find the distance d between them, then what you could do is you simply find the change in the y direction, and you find the change in the x direction. And then by Pythagorean theorem, you know that this squared plus this squared would be equal to d squared, right? So then if you take the square root of both sides, you would end up with d equals this. Does this make sense? Joyce, do you have any questions about the distance formula? Does everything we talked about make sense?
Yeah.
Okay. To just solidify your understanding a bit, I'm actually going to show you guys a little example here. So I'm going to exit the slideshow and bring us to Desmos real quick. Oh no, not scientific. Okay, so I'm going to show you guys a brief example, right? So let's say that you have the points, I don't know. Joyce, give me 2 random points in the Cartesian plane. Or Jasper, give me 2 points.
Random
What was that?
points.
Yep, just random points.
3, 4.
Okay. We need another point.
8, 1.
Okay. So we want to find the distance between 3, 4 and 8, 1, which is precisely the length of this line right here. So usually, if you don't have a ruler, you wouldn't really be able to know what the distance is. But since you know the Pythagorean theorem, one little cool trick you could do is that you can simply construct a right triangle by dropping a perpendicular and extending a horizontal line. And in particular, you want to make a right triangle here, right? Because you see that if you drop a line to here, in other words, if you connect the dots here, you would get a right triangle. So what you would do then is you take the x and y coordinates of the point closest to these 2 points, right? So here you would have 3, comma 1. And now that would give you this point. And then if you connect all of these, you see that, again, you have a right triangle, right? So you see that this here is a perpendicular right angle. And moreover, since we know the coordinates of these points, right? This is 3, 4, and this is 8, 1. We can figure out the horizontal distance and the vertical distance, right? We can figure out the lengths of these two. So in particular, let's figure out the vertical side length first. Let's figure out what's the change in y value. Jasper, do you want to give this a try? Do you know what the side length for this triangle is? This side length here.
Is it 3?
That's right, it's 3. because here's 4, here's 1, so obviously it's 3. Very good. Joyce, what's the change in x direction? In other words, what's the side length here?
Um, the top one.
Yeah, like the side length here, we want to find the length of this segment. Remember that this here is 3, this here is 8.
5.
That's right, very good. So indeed, we have 2 segments, 3 and 5, right? So now, Jasper, how can we find the length of this segment here? What can we do to find this segment, Jasper?
I'm not sure.
Okay, well, it's okay. By the Pythagorean theorem, we know that in a given right triangle, a squared plus b squared equals c squared, right? And moreover, we know that this is a and this is b. So now do you see a way to figure out c?
Oh, I get it.
Right, do you want to give it a try? Let's see.
Wait, can I go get paper or?
Yeah, of course. Go ahead. Joyce, you should give this a try too. See if you can figure out c.
Um,
Is it 34?
Yes, but almost. Well, it's like it's kind of 34, but also not, right? Because what you found is c squared, but we want c.
Oh,
But you're very close though. You're just
so
one thing and you're good.
wait, so it's 17, right?
Is that?
Wait, no, I don't think.
Did you guys get the answer? Jasper, you were really close. You just need one extra thing. Um, Jasper, did you figure it out?
I give up.
Okay, it's okay. Here, I'll show you guys. Jasper, really, you were really close, right? Because here you have, let's say, yeah, let's just call this hypotenuse c, the distance is c. So we know that 3 squared plus 5 squared is equal to c squared. Agree, right? So 3 squared is 9. 5 squared is 25. That's equal to c squared. If you add these up, you'll see that's 34. But we don't want c squared, we want c. So what you do is you just take the square root of both sides and you get c equals root 34. You can just leave it like this because 34 isn't a perfect square. But if you use like a calculator, you can see that the square root of 34 is 5.83. So in conclusion, the distance between the 2 points that Joyce selected is roughly 5.8 or root 34 to be exact. Does that make sense? So Jasper, you were really close. You just have to take a square root. Good? All right, okay. So why are we talking about the distance formula? The reason is that the distance formula allows you to understand the formula of a circle. So in other words, we can derive the general equation of a circle. Because you see, we talk about circles all the time, but it's good to wonder if you can actually put the circle on the Cartesian plane by writing an equation, right? And we can actually do exactly that, because you know that a circle is simply the set of all points that are equidistant from a center point, right? So quick example, if you have a point here called a center, the circle will be the collection of all the points such that it is equidistant from the center point. So for example, if I have the circle here, then every point on this circle, and by that I mean like literally every point, would have the same distance as all the other points from the center. So in other words, all of these little line segments I drew would have the same exact length, and that's known as the radius, right? So knowing that, we can describe all of the points on a circle using an equation, because if we know that the center point is some point hk, then we know that for any point on a circle, you can describe it by describing the distance between xy and hk and setting it to a constant, right? But this comes from the distance formula, because let's say that you have an arbitrary point xy, which is right here, and you want to find the distance with k, with the center point hk, right? As you guys just learned, the distance would simply be the square root of x minus h squared plus y minus k squared, right? Because you can construct the right triangle, and that would be the square sum of side lengths. So then, if we know that this distance is equal to some radius r, in other words, we know it's equal to some constant, we can set that equal, but then check what happens when you take the square of both sides. In other words, if you raise both sides to a power of 2, you would get exactly that, right? So then that is the general equation of a circle with center hk and radius r, right? Because this describes all the points that are a distance of exactly r away from the center. So this here is this here is the formula for a general circle. Does this make sense, Joyce, Jasper? Does this make sense? Do you guys have any questions? Joyce, is everything clear? Any confusion? Jasper, do you have any questions?
I don't think so.
Okay. Well, here, let me show you guys a few circles just to, like, again, solidify the concept. Okay. Let me exit. Let's get our trusty little Desmos. Not scientific. Oh, okay. So I'm just going to show you a bunch of circles. You know, if you solidify the understanding. Right? Okay. Guys, give me a center point. It's any random point on the Cartesian plane. Jasper, Joyce, give me a random point to be the center.
Wait, 8?
Well, you need a point, so another coordinate. 8, comma.
Oh, 8,9.
Okay. So then we know immediately that this would be the left side, right? Because we have center 8, 9. All right, Joyce, give me a radius. What do you want the radius to be?
You want me to give you a point?
No, a radius. Sorry, Joyce, the no worries is directed to Jasper.
Oh,
Just give me a random radius, random number.
12.
Okay. So now witness the magic. Check this out. You see this circle here? You'll see that the center is exactly 8, 9. Right? And then if you take any random line segment, so for example, from here to here, actually from here to here, the length would be exactly 12, right? Because this equation describes the circle with center 8, 9, and radius 12. All right, let's try another example. Joyce, give me a random coordinate. You can give negative coordinates too.
-7, 4.
All right, okay. So as you can see, since we have a negative coordinate, you would have +7 because you have minus -7, which turns into a plus. Okay, Jasper, give me a radius. 52?
No, like, can the number be like a big no?
Wait, sorry, you're lagging. Go ahead and type it because you're you're a little laggy. Yeah, as big as you want. All right, 98 it is. Okay, this is a bit big off the grid, so we have to zoom out. And now you see again, this is the circle with center -7, 4, and radius 98. In other words, if you take any point on a circle and connect it to the center, the radius will be 98, right? So it's a pretty cool little way to understand circles. But yeah, that's about it. And now we're gonna see the actual reason we're talking about this. And before we do that, I have to show you the actual equation for the unit circle. And that's this, right? So x² plus y² equals 1 is really the formula of the unit circle that we've been talking about all day, right? So, and again, it's just because x² plus y² happens to be equal to this, and this just describes the circle with radius 1 centered at the origin, right? So this is the unit circle. Again, the unit circle has equation x² plus y² equals 1. Hammer that in because we're gonna need it. All right, let me exit here real quick. Actually, I'm gonna leave this here in case we need it. So now, finally, we can build up to the proof, right? So again, the unit circle is simply a circle with radius 1 centered at the origin, right? So you can see that, again, its equation is simply x squared plus y squared equals 1. Right, then, since we know that we define cosine theta, sine theta to be the coordinates of the terminal point of an angle theta, it must satisfy the equation. So cosine squared theta plus sine squared theta equals 1. So once again, this is known as the Pythagorean identity. Does this make sense? Do you guys have any questions about this? Does this make sense? Basically, the idea is that since the equation of a circle, the unit circle is x squared plus y squared equals 1, and cosine theta, sine theta is a point on a circle, it must satisfy this equation, right? So if you plug these in, you would have this equation right here. And that is known as, again, Pythagorean identity. Does this make sense, Joyce, Jasper? Do you guys have any questions?
I'm good.
All right. Okay. So now we babbled about like 40 minutes on this little theorem here. So now let's do a little, cool exercise, or I guess demonstration on why we really care about this and why it's so important. So let's start by computing a few trig identities. So actually, let me stop sharing, and I'm gonna set up a whiteboard. Screen share. Okay. So let's start with a really simple example. Let's say that I have this triangle here. Uh-oh, I don't want to do that. I do not want to do that. Uh-oh. Okay, let's say I have this triangle here. And let's say that I know the side lengths are what? 5, 12, and 13. I know this doesn't exactly look like 12 compared to 5, but just bear with me. This is a right triangle, and this is x. So now we want to find sine of x. All right, go ahead, try this, and let me know what you get. What is the sine of x? Jasper, do you know the answer? Joyce, you want to give it a try? What's sine of x in this particular triangle? I do know. Okay. It's okay. Okay. So once again, brief review. Sine, cosine, and tangents is respectively SOHCAHTOA, right? Remember from last class. So, SOHCAHTOA. And so is opposite over hypotenuse. That's what O and H stands for. It's the opposite leg over the hypotenuse. Similarly, cosine is adjacent over hypotenuse, right? Because you can see the leg adjacent to x is 12 here, and hypotenuse is, again, 13. And tangent is TOA, so it's opposite over A, 5 over 12. So what is sine of x? Jasper, you want to try this? Oh, remember, SOHCAHTOA, opposite over hypotenuse. Here's x. What is opposite to x? My head doesn't want to work. But it's barely any work though, right? Because you just have to take the opposite over the hypotenuse. And what's the opposite? It's 5, right? And what's the hypotenuse? 13. So isn't opposite over hypotenuse just 5 over 13? Oh, okay. Well, Jasper, since we know now that it's not a lot of work, why don't you compute cosine of x? What's cosine of x? Remember ka, adjacent over hypotenuse. Jasper, any ideas? We just calculated sine. 12 over 13. Excellent. Exactly. It is exactly 12 over 13. Okay, Joyce. Now let's try tangent. What's tangent of x, Joyce? Remember TOA, opposite over adjacent. Just remember SOHCAHTOA, TOA, you'll be good for trig. Also remember that the hypotenuse is always opposite the opposite right angle, right? So it's always opposite the right angle. So in this case, 13 is equal to the hypotenuse. And here's the desired angle. What side length is opposite x, Joyce? What's the side length that's directly opposite of x? I'm going to give you a really big hint. Right? What? No, Joyce, what's the side length opposite of x? Like what's the leg opposite of x? What's the side length opposite of this angle here, x? 5, exactly. There we go. Yeah, it's 5. That's the opposite side. And what's the side adjacent to x? Joyce, I'm going to give you another hint. What's the angle adjacent to x? $12. Good. Right. So tangent is just 5 over 12. Right. Okay. So now let's put this to use. Put the Pythagorean theorem, identity to use by verifying that the square of this actually adds up with the square of this to 1. Right. Okay. So let's try this. So again, Pythagorean identity states sine squared theta plus, actually I'm going to use x since we're talking about x here. Sine squared x plus cosine squared x equals 1. So in our case, it becomes 5 over 13 squared plus 12 over 13 squared. And it should equal 1 theoretically. So let's try this. So it's 25 over 169 plus 144 over 169, which equals 169 over 169. And that is exactly equal to 1. So bam, we have verified the Pythagorean identity, right? So I think it's pretty cool because this means that even if you only know, 2 sides of a right triangle, you can figure out every sine function, cosine function, tangent function of the angle by simply solving for it using the Pythagorean identity. Are there any questions about this? Jasper, Joyce, any questions? Okay, well, let's finish with one more example, right? Okay. And in fact, I want to talk with a really basic right triangle that everybody should know. And that is 45, 45, 90 triangle. Okay. So in the 45, 45, 90 triangle, like the name suggests, it is a right triangle with 190-degree angle, in other words, a right angle, and two 45-degree angles. Right, so this is 45 degrees, and sorry, this is 45 degrees, and this is 45 degrees. And moreover, 45, 45, 90 triangles have a really special side relationship, because if the side length of this here is x and this here is x, and you'll notice that they're actually identical because it is an isosceles right triangle, and thus they have two side lengths that are exactly the same. So then if the side length is x, then their hypotenuse will always be x times root 2, right? Like it will always be this. So if x is 3, the hypotenuse will be 3 root 2. If x is 4, the hypotenuse will be 4 root 2. Okay, so now let's do a little computation. Jasper, what is the sine of 45 degrees? Joyce, do you guys have any idea? What's the sine of 45 degrees? Jasper, do you have any ideas? What's the sine of 45 degrees? Yes, 45, but what's the sine of it? Like, what's the sine function of 45 degrees? I don't know. Well, again, it's just so katoa, right? Just sine is always opposite over hypotenuse. So Jasper, in this case, let's say that we took this angle just for the sake of solving this. What is the side length opposite of 45? Like, what's the side length opposite 45? Just tell me the opposite side length. Sorry, what was that?
Wait, is it 90?
Not quite, because again, we're talking about the opposite side length, right? So if 45 is the angle here, you go directly opposite, and that gives you a side length of x, right? So that's the opposite side. And when you put it over the hypotenuse, you put it over x root 2. So you would have x over x root 2. So it's equal to 1 over root 2. Right, that's sine. Okay, Joyce, let's try this one. What is cosine of 45 degrees? Again, cosine is adjacent over hypotenuse. So Joyce, what's the cosine of 45 degrees? Remember, adjacent over hypotenuse. Take the adjacent side length to 45 degrees and put it over the hypotenuse. Look at the sine example. The sine is opposite over hypotenuse. Now we want adjacent over hypotenuse. So what is that? Well, Joyce, you successfully gave us the adjacent side, right? That's right. The adjacent side length is x, but what's the hypotenuse? What are we putting it over? What's the length of the hypotenuse, Joyce? I do know. Remember, the hypotenuse is just opposite the right angle. What's opposite the right angle? I'm pointing it. No, Joyce, what's opposite the right angle? What's opposite the right angle? Joyce, the side length opposite the right angle. Okay, it's just x root 2, right? It's x root 2. Cosine of 45 degrees is adjacent over hypotenuse, and that's x over x root 2. And once again, that simplifies to 1 over root 2. So now once again, let's put this to test against the Pythagorean identity by squaring them and adding them together. So if you square both of these, you would end up with 1/2 plus 1/2 equals 1. So once again, we have demonstrated the Pythagorean identity. So once again, you could have solved for either one of these using the Pythagorean identity. So are there any questions about this? Any final thoughts, comments, intrigues, bothers, puzzles? Jasper, Joyce, do you guys have any remaining questions? Okay. Well, if not, that's really all we have to cover today. Let us know if you have any questions. We already sent the slideshow in a group chat, so if you guys want to look at it after class, that's fine too. But otherwise, have a good weekend. Bye.